Good morning, everybody, and thank you very much for joining us today. My name is Lisa McKenzie. I'm the Marketing and Communications Manager at the European Marine Energy Centre, also known as EMEC, in Orkney. And today, along with my colleagues on the call, we are going to provide some insight into the development of Orbital Marine Power's O2 tidal turbine. The O2 development was supported by the European Union's Horizon 2020 Research and Innovation Programme in a project called FloTEC. Now, that project has now come to an end, so the project team were really keen to share some of the lessons learned and innovations from the project with you. So I'm joined today by James Murray, Programme Manager, and William Annell, Mechanical and Structural Engineering Manager at Orbital Marine Power, Michael Bowman, Business Development Manager, and Matthias Hoffman, Design and Engineering Manager at SKF, Chris Poyner, Power Conversion Business Manager at ABB, Paul McAvoy, Chief Technical Officer at TFI, and my colleague Caitlin Long, Environment and Consent Specialist at EMEC. So, as mentioned, we'll be delving into a number of innovations that were progressed in the FloTEC project, including the structure and blades, the main shaft unit and mechanical design, the power conversion systems, mooring dampers, environmental monitoring, as well as the construction and deployment of the O2, which is now operating at EMEC's tidal test site at the Fall of Warness in Orkney. So we've allowed some time at the end of this session to answer some of your questions. So please do be submitting your questions via the Q&A function in Zoom throughout the event. You can also upvote which questions you've seen from others that you'd like to hear answered. So please do put it into the Q&A function and not the chat function, and that'll mean that we can see all of your questions coming through. So thanks again for joining us, and I'll pass over to James Murray at Orbital Marine Power to get us started. Over to you, James.
Thanks very much, Lisa. So when the FloTEC project was originally conceptualized more than 6 years ago now, the intention was to build upon our first full-scale commercial prototype, the SR2000, and to deliver a number of targeted cost reduction innovations. Now, following an honest, I suppose, engineering appraisal of what was required to truly move the sector, to move the technology towards a commercially viable generating solution, it was decided to go beyond the original target innovations and to deliver something even more ambitious. And that is what we see today encapsulated in the O2 tidal turbine, which, as Lisa said, is now operating at the European Marine Energy Centre in Orkney in Scotland. And one of the key challenges we set ourselves, and one of the key enabling features of the new model is full access capability to all the devices, components and systems on site with manned access. To achieve that, we completed a significant structural reconfiguration of the overall platform and design. In the process of the project, we delivered a wealth of new intellectual property, including know-how, but also a number of patents generated and secured around the key enabling features of the technology. And we also delivered a minimum, depending on what site you look at, of 20% reduction in the levelized cost of energy of our technology, and we believe the tidal stream energy sector as well. I'm just going to highlight some of the key innovations, not going to go into too much detail because my colleagues and the project partners will do so later on in the webinar. The first thing to say is we increased the rotor diameters of the machine by 50%. We now have a 50% increase in swept area, 600 square meters of swept area in total. We incorporated pitch control for floating tidal energy, which responds to both the tidal currents in real time, but also the the wave conditions as well to optimize power performance. We incorporated gull-wing leg configurations to bring the powertrains, the blades, above the waterline for on-site access and maintenance. We installed the machine with modular gravity anchors to ensure that all installation operations could be carried out with low-cost, locally based work vessels. We improved both the mooring and electrical connections, and we also transitioned to commercially compatible power conversion such that the unit can be integrated with larger tidal arrays. We also performed a number of significant design changes to ensure there is future proofing for both ongoing innovation, be that scaling of powertrains or blades, and also compatibility with volume manufacture. Now, all of this was delivered with an entirely pan-European supply chain. A number of our suppliers to the overall turbine are here today, but there were also suppliers from Finland, from the Czech Republic, from France, from Spain, from Sweden as well, that were involved in delivering key components to the overall project. So I think, and hopefully you'll agree after today's webinar that the project is an excellent showcase of what Europe's industrial and research communities can do when they come together with the right support. And now, without any further ado, I'm going to pass over to Lisa, who's going to present and launch our final end of project video. Thanks, Lisa.
Our goal was to drive down the cost of tidal stream energy through the engineering and performance testing of a series of innovations on the company's world-leading tidal technology. We had to be bold with our vision, and we had to push the limits of engineering and imagination to deliver the right solution. Through that, we came up with the O2, a radical design the likes of which this world has never seen before. The floating superstructure is about the same length as a 747 jumbo jet with 18-metre-long legs, holding 100-ton nacelle assemblies at a 14-metre depth. With rotor diameters of 20 metres, the O2 has some of the longest blades ever seen on a tidal turbine. These give it a total swept area of over 600 square metres, and at full power, the turbines will be able to generate 2 megawatts of predictable clean power. Each of the mooring lines used to anchor the O2 is strong enough to pick up 50 double-decker buses. Now installed at the European Marine Energy Centre in Scotland, the O2 is generating clean, predictable power into the UK grid and demonstrating key aspects of its performance are in line with its design. As the world's most powerful tidal turbine, the O2 is expected to trigger a step change for the tidal energy sector. The FloTEC project was an instrumental step towards powering millions of homes with the clean power of the tides.
Hi everybody, my name's William Annell. I'm the Mechanical and Structural Engineering Manager here at Orbital Marine Power. I've been with the company for quite a long time now, for about 12 years. And my role is to deliver the mechanical and structural side of the turbine from the concept and engineering stage through on to procurement and manufacture. Today I'm going to be presenting some of the high-level innovations that we were able to deliver via the FloTEC project, mainly focusing on the changes that we made to the overall structural configuration and to the rotor assemblies. So one of the earliest design goals was to make the rotor assembly, the overall structural configuration, the legs, nacelles, this assembly process as modular as possible. So we designed all the major structural components so that everything could be road transportable and transported by road to the manufacturing site. This allowed us to adopt a very flexible tendering strategy so that we were not tied to any specific facility or skill set. This modular approach allows for the assembly work to happen in a number of locations, be it at the main assembly site or closer to the tidal site where we have the option of installing the nacelles and blades in the water. We also designed the superstructure so that it could be sectioned up and packaged off and allow us to target the work scopes to the most diverse range of bidders. And this is to theoretically get the best price. So for the superstructure alone, we tendered to 7 different facilities, and we ended up using 2 of them. This made us achieve what we believe was the best price for what the market could provide at the time for a single device. But however, it did make the contracting strategy quite complicated. So you can see here, this is a kind of roadmap of the build. It's only got the kind of some of the high level packages in here. There was a lot of other elements to the project that's not shown. But the major bits that are here is the superstructure fabrication. So that was carried out by Texo in Dundee with the support of Great Fabrication in Cooper. The skids, which we did ourselves, the nacelles and hubs, which were by SKF, and the blades, which were ACMC. So all of these work scopes involved critical physical and contractual interfaces. So we had the aim to simplify the contracting strategy and just use one contract template across all the bidders and all the partners. And this was to minimize the project management headache. But so in total, we had about 10 contracts, and we used the same contract template across 8 of them. So this meant that we could just apply the same understanding and same mechanisms to as many different situations as possible. One of the other key objectives and features, and this one is probably the most striking aspect of the turbine, and it's the retractable rotor legs, so the gull wing mechanism that was mentioned previously. So in the SR2000, we had a hinging mechanism that moves along the machine and tucks the rotors up underneath into a stowed position. And with this machine, we changed the design quite significantly so that the legs come up perpendicular to hull and move out to the side. So the primary reasons for this were to enable on-site access. So it brings up the nacelles up to the waterline, and the nacelles and hubs then breach the surface via using a hydraulically actuated linkage system. So when the rotors breach and then the nacelles and hubs come up, you can then access the nacelle and get on board to carry out small maintenance activities, inspect for wear and other different elements of maintenance. So doing this on site helps considerably reduce our cost of energy. The other main reason for doing this change was to enable larger rotors. So the previous design had some space constraints that meant that increasing the size of the rotor would sort of create a mechanical disadvantage in the system. So by going out to the side, we gave ourselves a lot more room, and we're able to go up from 16 to 20 meters, enabling the largest ever swept area on a tidal turbine. So the design is also scalable even further, so we can enable even larger rotor still, or accommodate larger loads. The next key feature is the Depictable Blades. This technology was developed in conjunction with our partners SKF, based in Sweden and Germany. By pitching the blades, we can optimize the energy extraction of the rotors throughout changing flow speeds. And another main advantage is that we're able to shed power more easily as we approach rated speed. So this makes the whole process of controlling the energy extraction more controllable. This means that the peak mechanical and electrical loads can be reduced significantly, and the overall size and capacity requirements of the drivetrain, power electronics, and other elements of the structure can be reduced. So you can see here, this is us on site in Dundee, carrying out some commission activities. All this was pre-tested and inspected before arriving at site. So this is us doing the integration work into the hull. So theoretically it should work first time, but that's never the case. But at least we'd worked out most of the gremlins before it had arrived. So we've also used commercially compatible electrical architecture that's based on proven technologies. And we've built on learning from other industries such as offshore wind. This has allowed us to take advantage of the existing supply chains, and Chris Poyner from ABB will elaborate on the technical side of the electrical architecture in his presentation later on. The last key feature I'm going to talk about is the modular anchoring system, which is a gravity-based system. The anchors used on the previous machine, the SR2000, were also gravity-based. So there was an environmental and an economic incentive to reuse the ballast for the O2 anchors. So we designed anchors that could accommodate a range of ballasting options. This allowed us to recycle the old ballast and also use scrap steel to make up the rest of the required mass. And if it turns out that the coefficient is lower than anticipated, we can simply add more ballast to make up the required holding capacity. The anchors were also designed to be totally installable using small workboats, and this dramatically reduced the cost of installation works and greatly increased the flexibility of the installation procedure by using locally available vessels. And you can see in the picture there, there's a multi-cat based in Orkney using our lifting frame, which was used to install the ballast. So this brings me to the end of a short snippet into the main FloTEC related innovations of the O2, and I'll now pass you on to Michael Baumann and Matthias Hoffmann from SKF, who will discuss the main shaft unit and mechanical design elements of their work package.
Thank you, William. So good morning, everyone. My name is Michael Baumann. I'm the commercial lead for SKF in Ocean Energy. And the picture, which you can see here, shows you well the end result of our FloTEC scope of work, one of the fully integrated powertrains we delivered as part of the project. In order to start, we would like to give you a very quick introduction into SKF. SKF supplies more than 40 industries globally. So SKF is globally leading in the rotating equipment area and stands for reliable rotation. SKF transfers its knowledge from ocean energy or to ocean energy from synergistic industries such as marine, wind, oil and gas, and hydroelectric to make use of proven products where possible. Also in that project, we used an awful lot of knowledge and products and services from, for example, the marine, wind, and oil and gas sector. SKF offers includes generally a broad product range of bearings, seals, lubrication systems, and the full integration of them into holistic system solutions, to name only some of the main product and service areas we provide to our customers. In tidal energy, SKF is specialized in pitch and yaw, rotor shaft, and gearbox applications, and it's fully integration. In FloTEC, the main job for SKF has been in Work Package 8 and Work Package 9 to develop, to design, manufacture, and assemble the main shaft bearings, sealing systems, bearing housings, and shaft to provide a holistic plug-and-play main shaft unit. In comparison to the SR2000, the previous tidal turbine from Orbital, the current main shaft unit increased by 200% in size and by 400% in weight, mainly due to major design changes of the powertrain and also due to the increased installed capacity of the existing turbine. Key enabled by the FloTEC project, SKF increased its design engineering efforts jointly with Orbital to ultimately design, engineer, and to assemble the entire fully integrated powertrain. And now I will hand over to my colleague Matthias, who will introduce you more to the technical details.
Good morning all, my name is Matthias Hoffmann from SKF in Germany. I am Design and Engineering Manager and from SKF perspective responsible for the drivetrain development with today's focus on the so-called bearing mainshaft unit. On the right top picture you see the whole powertrain, we call it. Left side is a rotating pitching hub, then we have the bearing unit in the middle, and then the nacelle is starting until the end cap on the right side. It's a big machine for us, and the picture below shows you the basic principle of the drivetrain with MSU, main shaft unit, to take the hub loads and transfer only rotational drive torque to the gearbox. It's a speed increaser to drive the generator. It's basically a 1.1 megawatt drive, you can say, and it's designed for water level to a maximum level of about 30 meters with a selected dynamic and static seals. Two-bladed machine, and the blades can be turned basically about 360 degrees on low speed. And on the picture you see the connection box to the side arm of the swimming of the floating platform. Basic design principle, and this was done in very tight and very excellent cooperation with Orbital, was the modular concept, a modular assembly and repair friendliness we had on our list. This was the design driver. During the development of the main shaft unit, we started basically on a white paper. That means we pictured a first rough rotor shaft, bearing selection, two-point bearing selection housed in two single housings or two joint housing. We started with first rough bearing calculations, as you see on the right top picture, considering all the load input, also the gearbox hanging at the shaft end to fix the bearing type, the bearing size, and the load ratings of the bearing. This is a starting point. And parallel, we did first shaft calculations, fatigue strength calculations for all load conditions. And we played also around with different shapes of the shaft, also different materials to analyze, to find the optimum solution. On the right side, you see a challenge we had during the project with a big overhang of the hub. For sure, the outer bearing is high loaded, and it's known subject to us that a rolling element can have an uneven stress distribution. And this is pictured basically in calculation programs over the roller length. And there is an allowed limit we would accept. And this is also the basic to go on with further bearing lifetime calculations and so on. It was a special development, also in that aspect, that the bearing housing outer diameter is closing the nacelle, the big cylinder. The bearing itself are kept on a smaller diameter. There is an included seal in the bearing unit divided from the ship propeller application. And the challenge also here, big hub loads, big blade bending moments acting on the bearing, and also what I like to say, a dominating axial thrust load coming from the water stream, what is relevant for also again for the bearing selection and consideration of the bolt connections. During the project, we covered increase of the complexity. Also a lot of products and features were integrated, like sensors and lubrication system topics. And the originally smaller unit was at the end larger and higher production costs as formerly expected, we can say. One of the learnings in the past, it's basically a modular drivetrain concept with a rigid connected gearbox at the shaft end. And we think from our perspective, this is suitable for the 1 mega class, but can be also upscaled for bigger turbines if needed. As a product itself, the main shaft unit fits very well to our factory, to our company. Learnings about the main shaft unit, and this is starting now with the first offshore field learnings. We have an installed condition monitoring system. This is just a record about vibration behavior, temperature recording over time. This gives us a good impression about the situation of the bearings, on what temperature levels they run, and has also influences to the viscosity. And this is also relevant for the calculated lifetime. We just collect these experiences or these measurements, and very helpful for us today. In long term, it's about the seal performance. The seal is called Simplex, what you see here on the right side. It's a subject that seals will also wear over time. And we need this field data to say how long, how many years this can run and when to repair it. The gearbox is connected to the rotor shaft via so-called SKF OKCK coupling. And also here, we like to check the performance. It's a stiff coupling. But we have also, the gearbox has a weight of about 10 tons. And it's important that we have here also a good observation of this coupling and not any micro movements. Corrosion behavior is a topic we like to further observe on the rotor shaft, bearing housing, and also about the static seals. It's not only about the surface itself, it's more, we have a lot of flanged contacts and static seals, and here the corrosion is very important to keep an eye on this. And just now we are further involved in service aspects, also prepare possibly repairs for the future. We possibly need some special tools for it. Spare part management is also on our list today. And also in long term to see and to check the theoretical calculated lifetimes if we fulfill this in reality. Next slide. That's it from SKF side. And now I'd like to hand over to Chris from ABB.
Good morning all, thank you very much for joining. So I look after the power conversion business for ABB in the UK. We've been working with Orbital Marine, previously Scott Renewables, for a while now, so we're quite au fait with the equipment. But why ABB? As you may know, we're a leading global technology company. We're located in 100 countries. I won't give you the sales spiel too much, but we're global, we're everywhere. We've got proven technology in the renewables industry. We've got components in approximately 40,000 wind turbines, which, as you'll know, is probably the closest industry to tidal at the moment that has a volume to it. We've got diverse tidal industry experience. We've been working with a number of suppliers in the tidal industry, and to be honest, it's an industry that doesn't scare us. We've got the product portfolio, and we've got the gumption to go for it. Like I said, we're heavy in wind, so for us, it's an extension of that industry. We also have extensive and relevant product portfolio. We've got, the power electronics, as you know, power conversion. We also do robotic painting systems for wind turbine blades, etc. Could easily be utilized for vessel hulls. Control systems, the power part control, the local control, PLCs, anything up to, full systems. And also remote condition monitoring. So we're able to monitor equipment like this when it's offshore. It's been touched on previously by SKF and by William, but obviously with a device like this, you don't want to be doing unnecessary maintenance. You want to be able to monitor it remotely, check it's working as it should, and take relevant maintenance interventions as and when required. And at the bottom, we also have a global service network, which is very handy when you've got a device such as this, and you could be installing it in EMEC, you could be installing it in Korea. It's good to have global support. So that's why we're involved. Now, for ABB, for the FloTEC project, which we're talking about today, we had three main objectives. One was to develop a centralized MV power conversion topology for tidal arrays. You will see we didn't quite achieve that at the end. I'll come on to that shortly. To deliver a design specification for the conversion system for the SR2002, which is now the O2 turbine, and a 4 megawatt array at EMEC. So basically, we had to do a design for one device, but allow it to connect to two devices at the EMEC berth. And also the third point was to consider the effect of energy storage in this topology. So the electrical design requirements for the turbine were, it has to be fully grid compliant. So obviously this is the Orbital product. They want to be able to sell this to anywhere in the world, and it needs to be able to connect into a grid because ultimately it's there to generate power. It also had to be marine rated. This is a floating vessel, so it's not shore based. So there's certain impacts on the vessel that the equipment has to be rated for. Obviously, as we mentioned before, there's two separate generators, so we have to be able to handle two generator inputs. One common grid connection output at 11,000 volts. So basically, you've got the two generators coming in, and we just need to give three phase 11 kV out at the point of connection to the cable to the shore. This is a new requirement we had compared to the SR2 2000, which is the fact that we have to be, because they now are introducing pitch control into the system, we have to rate it so that the absolute max limit of the equipment relates to pitch control failing in the worst case scenario, in the worst case Cs. Now, this should never happen. And the guys from SKF will, they'll reassure you on this, that it should never happen. But if you didn't consider it, you wouldn't be doing your job. So that was quite a difficult consideration. And also the turbine output, it needs to be suitable for multiple arrays. As we said, for this, it was based on 2, but hopefully as the industry moves forward, you're looking at multiple devices and you need to be able to connect them simply, easily, and economically. So electrical design considerations. So we were told what they needed, and then for ABB, we had to look into this. So we were asked to look at a centralized MV system. Now, as you guys will know in the industry, medium voltage is never a cheap solution. Low voltage is much more prevalent. So we had to balance off the efficiency versus the cost. Obviously with MV, higher voltage, less losses in theory. Low voltage is more readily available, and generally it's a cheaper product. So you're trying to weigh those two off. Single drive versus multi-drive. Now this is a bit of power conversion topology. So basically a single drive, you have one unit that does one generator, and so it's got a generator in and a grid connection out. A multi-drive, you have 2 generators in and 1 grid connection out. Now, so you're looking there, there's obviously a cost saving by having the multi-drive, but you're lacking the redundancy. Now, for a device like this, for a single device, you want some redundancy. For an array, you can probably afford to lose a device for that period if there's an issue. So that's something else we've had to consider. The third point is wind versus industrial product. ABB as a supplier, we have the same variation of power converter we use in industrial drives everywhere, spinning fans, motors, cooling pumps, anything like that. And we also have a wind portfolio, which is a specific industrial product we reconfigured for the wind market, which is a big industry for us. So we have to look at which is the best fit. Are we best using the wind, which is already configured for grid compliance, etc., but comes in dedicated sizes? Do we use industrial products, which we can pretty much configure? Okay, so we've had to look at weigh those two off. Sizing, I mentioned the pitch failure extreme conditions. We've had to really think about how to size it for worst case scenarios. And array compatibility, I've mentioned that again. It's basically, you've got to be able to connect multiple devices to an array. So the electrical design outcomes, I'm keeping this quite high level. There's Q&A at the end, or you're welcome to contact me if you have any specific questions, but for now it's quite high level. So basically we looked at the turbine power rating, 2 times 1.1 megawatt, but there is a bit of headroom as we said, but ultimately it did not make an MV solution financially viable. Low power MV converters are expensive and not readily available. Our personal range, the PCS 6000, generally 4 megawatts is the kind of the sweet spot, and that's for a single turbine. In the wind industry, traditionally, we're losing low power drives up to quite high power ratings. It's a very traditional way of working in wind, and obviously wind is the closest industry to tidal for this sort of technology. A step-up transformer may be required anyway. Now, in principle, we could make an MV power converter, MV generators on the vessel, but depending on where it goes, it might go to a different country and it needs a step-up transformer for different voltages. So, like I said, the benefit of not needing a step-up transformer of an MV solution was not necessarily worthwhile for this one. Efficiency, like I said, medium voltage, less losses in theory, but given the short cable runs, it's a payoff on cost versus cable run length. And also LV equipment is easier to maintain for this application. Now, when you sell any MV product, it's very specific about who can work on it, how they're trained. LV is a little bit less, you're less constrained by who can work on the equipment, should we say. Obviously, you still have to be trained, you still have to have the correct paperwork. There's no question there. But for something remote like this, where you access it by a vessel, LV is just easier for a day-to-day to live with. But the comment at the end, however, as the power output or array size increase and technology moves forward, this may change. We're always developing new products. We're working on new MV converters, and if we have one that fits this power application in the future, that may be more relevant. But like I said, for this project, we've stuck with LV because it was the best fit. So This is a very simplistic drawing for you guys, but this kind of shows what we supplied for this one. So we've got, starting at the generators, they're basically squirrel cage induction generators, sorry. Standard product for ABB, very similar to our motor products, but slightly reconfigured. The power converter, you can see there, it was based on an ACS 800 liquid-cooled multi-drive from our industrial portfolio. I mentioned before about redundancy versus cost, basically. And for this one, we having previously provided separate drives, this time we provide a multi-drive. So it's got 2 generators feeding in and 1 voltage feeding out the grid side. Okay, and what that means is then the transformer is simpler because it's a 2-winding transformer, whereas if you have a separate converter, you have to have 3. I won't get into too much detail. Like I said, if you've got any questions, please ask at the end. And so, yeah, so then we've used basically a glass fiber reinforced dry type transformer, so a marine transformer, but dry type, nothing too particularly clever. It's liquid cooled, which for a transformer is, you know, it's not as standard, but it's pretty standard for us. And then we've got on the front end, we've got some marine rated Safe Plus switchgear. So moving on, another part of our scope was energy storage. Now, as part of this, we did a big study and the report was huge. It would take me about 3 weeks to present it. But basically, we were looking at the feasibility for energy storage for the site at EMEC. Now, from a tidal turbine point of view, they obviously generate at certain times, and other times they're not generating while the tide is reducing and then going the other way. So to ensure the maximum capacity factor of the cable, because obviously the cable is a very expensive investment, you want to have that running at full current all the time. It would make sense to have the energy storage offshore. But as we know by looking at the turbine itself, trying to do that, it adds cost and technical risk, so it's not really feasible. Secondly, on researching this project, we realized the EMEC local network has a surplus of generation at the moment. Obviously, you've got the EMEC facility, it's Orkney, it's not a big area. And basically, there wasn't a demand for the energy. So to invest in an ESS as part of this project did not make commercial sense at this stage. Now, as we move forward with decarbonisation of vessels, etc., and you may start having hybrid electric ferries that are going to consume more and more, it might be feasible in moving forwards, and you could balance the load out that you're generating by tidal. But ultimately, as it stands, when we looked at this FloTEC study, it was not justifiable, really. As I've said there, to justify energy storage, you need more local demand, which is not really something you should be saying at times in net zero. But if that demand develops through the green industry, then it would then be worth looking at adding something onto this system. And the point at the bottom is energy storage would be beneficial for certain tidal arrays. Now, for EMEC, we've got 1 device there at the moment, potentially could go to 2. If you're looking at 10 devices, you can integrate, if you had like a central collector station or something, you could integrate energy storage to maximize the capacity factor of the cable. So like I said, on this one, it wasn't worthwhile. Moving forwards, there is definitely a place for energy storage in tidal generation, purely by the predictability and the fact that you don't generate for a certain period of time. Which takes me on to my last slide, lessons learned. So we learned that low voltage equipment still offers the best cost efficiency benefit at this power level. As I said, we're generating new product, we're working on new products, as other suppliers will be. This might change, but as it stands, the low voltage product is our win product, it's a volume product. It suits the requirements of the orbital turbine. So as it stands, it was the best fit. By using standard components, architecture can be scaled as the power output increases. The benefit of our equipment is the generators come in frame sizes. So as the power requirement goes up, you go up a different frame size. We have considered PM technologies, direct drive, getting rid of gearboxes. As it stands at the moment, it wasn't sensible for this project, but moving forwards, that's definitely something we'll consider. So like I said, the benefit of this is as the power goes up, the product goes up, but it's still the same product essentially that we're using. The third point I've kind of labored enough, so I'll just say it once more. Energy storage, it can add value for the right project. And finally, utilizing the existing wind industry technology is the best way to try and reduce LCOE for tidal projects on the power conversion side. Traditionally, obviously with tidal, you want to follow wind. Wind, the power's gone up and up and up, but there's still quite healthy demand in the kind of 2, 4, 6 megawatt projects using LV converters, and ABB, we have a good business in that, and that means that we're able to have a product that is cost competitive for the tidal industry. So like I said, at this power range, that's quite a good option. And like I said, we're here for LCOE. If we could have the best product in the world devised for every project, but if the cost doesn't meet and tidal can't generate the revenue, it's pointless. So like I said, for ABB's point of view, following wind industry technology does seem to be the solution at the moment. But as powers change, as architectures change, never say never, but that's where we sit at the moment. thank you very much for listening. Any questions will be asked at the end, if that's okay. I'll put them in the Q&A and we'll look at them at the end. And in the meantime, please can I hand over to Paul McAvoy from TFI.
Good morning. I'm going to present today about the mooring dampers, which were developed as part of this project. So if I kick off, I'll start then by talking about the project objectives. So the purpose of the mooring dampers was to reduce the cost of the mooring system. And we were seeking a 30% cost reduction across the project using these mooring dampers. It was a very ambitious goal using these dampers because they're an innovative new technology with a unique response that has never before been delivered in a component. There was also a huge increase in the component scaling over the life of the project, going from almost 4 orders of magnitude in terms of the loads that they needed to manage from the scale of the product we were at the start of the project to what we needed to deliver towards the end of the project. So our development cycle was to use industry standard simulation tools to predict the behavior of the device with and without the mooring dampers. And then we would use those tools to optimize those mooring dampers and to enable us to drive down those loads and the fatigue. There was a huge challenge throughout the project because, as you've heard, in parallel, the platform itself was undergoing many, many changes, such as the mooring layouts, the shape of the platform, the feathering of the blades, the control systems. And each of these changes would then require us to redo and revisit all of the modeling work that we had been undertaking. In parallel with the modeling work, we chose to use a 1/3 scale prototype to allow us to undertake multiple test and optimization cycles. And we'd use these cycles to test and validate the material properties of the polymers and the specific shapes we're using in the dampers and the physical spring designs, and iterating and improving on those from cycle to cycle. So at the start of the project, or just before the start of the project, we had completed some flow wave testing shown in the images in the top left there to validate the concept in the flow wave tank in Edinburgh. The left-hand side, or sorry, the right-hand side image then shows the first iteration then of that 1/3 scale prototype product. And it was based on a fairly heavy metalwork structure and loose individual polymer components stacked on top of each other, then that would be compressed during operation. And the image then of the video, sorry, on the bottom is showing that first 1/3 scale prototype being tested at the Dynamic Marine Component Test Facility in Exeter with a whole series of sensors on it to help us understand how it's working and its behavior. We then moved on to a second iteration of the 1/3 scale prototype. And here we had dramatically improved the metalwork design. So we had lightened the amount of metalwork very substantially. We'd stiffened it. So we had changed from bar type approaches to using beam type approaches. And we made it much, much easier to fabricate, which would help drive down cost. We had also welded the polymer components together for the first time, as we had seen in the first iteration of testing, that this was really required to ensure we got the right response curve from the component to give that 2-step response. We then moved on to a third iteration. And in this third iteration, we further improved the metalwork, making it lighter again, and in particular focusing on the ease of fabrication and the cost of fabrication. We also made major changes to the molding techniques we were using for molding the polymer parts and the welding techniques we were using for welding the parts together to ensure that we could survive very, very high load compression on the components with no substantial fatigue damage to the welding or the components themselves. The video in this, by the way, is showing a real-time video of the behavior of that component in a storm sea state. The previous video in the second iteration was showing accelerated testing. And we use both of those type testing to validate performance, but also to generate fatigue life information. So post the trials and testing in the DMEC test facility, we then brought the components to the EMEC test facility, where we've deployed them on a particular system setup to validate very high load performance. So this is part of our certification work and specifically designed to answer the question, what happens if the loads actually exceed the design loads you thought you were going to have? And in this scenario, we've designed the system so that we get 50-year event loads on the component multiple times over 3 month sort of period. So moving on then to the full-scale product. So it's worth stating here that it's a very unique product. So the part thicknesses that we're using here are well in excess of the largest injection molded products made, which typically are wheelie bins, for example. And the engineered copolymers we're using have never been made at this scale. So because of that, we basically needed to become world leaders in large volume, thick-walled polymer fabrication. And we spent over a year working closely with DuPont, who are the material suppliers, making large brick and breeze block sized products to allow us to validate the different fabrication processes and the change in mechanical properties, both across processes, but also within a single product, varying with, for example, thickness or direction of injection of the mold and so on. And we also had to spend well over a year on the welding techniques before we had a usable welding approach, undertaking a large amount of research and development work and trials and testing to figure out what way to connect those individual polymer components together to form the overall damper. So once we completed that work, we were then able to design the mold itself. So we used tools such as mold flow shown in the drawings here to design the mold block itself. And we packed the mold block with a lot of additional functionality, which would allow us to test new manufacturing concepts and features. And on the bottom right, we see the mold itself. And on the bottom left, we see an example of the actual hot runner system that went into that mold that allows us to choose exactly which parts of the mold we fill with polymer at which point in time and how to pack that with the polymer. So over the summer then, we fabricated these large full-scale products. And you can see just a picture on the left there of those individual shells, which weigh about 70 kilograms each on the mold. And then those are stacked together to form the full spring, as shown in the picture on the right. This one's just stacked. In reality, of course, they're being welded. So the full spring is a welded solid component. So coming back at the end then to ask, well, did we achieve what we aimed to achieve? Well, we did indeed demonstrate 30% peak load reductions and 20% fatigue reductions. The load reduction is actually about 50% below where we were at the start of the project. But as already discussed, many of the innovations on the platform, specifically around things like feathering of the blade and so on, allowed it to actually reduce the loads it was seeing itself. So we're only seeing about 30% load reduction on the current version of the platform, but it's still very substantial and it delivers that 30% cost reduction. In parallel to that, we're also being able to demonstrate a much smaller footprint. So by putting the elongation into these components within the mooring line, we're able to reduce the length of those catenary lines, which allows for a tighter packing of these products within any particular space in the ocean. They also have a reduced environmental impact with far less clashing of the products or of the chains and the mooring systems on the seabed, so cause far less environmental damage. So thank you very much for that. And I'll pass on now to Caitlin Long from EMEC, who will talk to you about the environmental monitoring.
Hello, thank you very much, Chris. So EMEC was leading the environmental monitoring work within the FloTEC project. And through that, we have developed a comprehensive environmental monitoring programme that was developed and approved by regulators and statutory nature conservation bodies. The programme is a live document and will remain beyond the FloTEC project to ensure consent compliance. Although the programme assessed and identified mitigation, monitoring and management measures for a wide range of environmental impact pathways, there was 4 particular impact pathways that were focused on throughout the FloTEC project. These were disturbance and displacement, underwater noise, collision risk and seabed impact. I'm now going to pick up on a couple of those and present the key findings from the project. So focusing down on acoustic characterization. So an acoustic signature is associated with the operation of the device and the mooring system. Characterizing this signature is essential to understanding whether there is potential for the device to cause injury or change the behavior of animals and affect the communication between them. We are particularly interested in the effect on fish and marine mammals when investigating noise. EMEC deployed our drifting acoustic receiver and tracker system in the fall awareness, undertaking over 50 drifting campaigns this summer. The surveys have been completed in line with the International Electrotechnical Commission Technical Specification 62600-40 for the acoustic characterization of marine energy devices. At 25% rated capacity, the O2 was clearly detectable between 10 and 1000 Hz, with a frequency of 40 decibels above ambient noise recorded compared to our reference site, and then 10 to 15 decibels compared to when the device was not generating. This is within the hearing ranges of seals and porpoises. So I'm now just going to demonstrate what the device noise is when it is not operational. So you might need to increase the volume in order to hear this. That clattering that you can hear is the mooring system. Now, this is the operational device at 25% rated capacity. You can hear a background hum, which is the device operating, but you can also hear the clattering of the mooring system in there as well. The species' ability to detect the device is not actually necessarily a negative impact, and this would actually support the animal's ability to perform evasion and avoidance behavior. However, it is important that we understand if these small-scale effects that we might see in terms of avoidance may have longer-term effects on a habitat exclusion or barrier effects, and they have a consequence at a population level. The other impact pathway that was considered in the project is, let's move on, there we go, collision risk. So collision risk is, environmental collision risk is the potential for a marine mammal or diving bird or fish to interact with the blades of the device. It's expected that the animals will employ avoidance and evasion behavior, and therefore this type of impact is very unlikely to occur, and if it does occur at all. Within the FloTEC project, we've been undertaking modelling to assess the potential for the theoretical encounter rate for key bird and marine mammal species using site-specific density estimates. We've built software in Shiny for R to automate the modelling and allow us to investigate whether device parameters are, which device parameters are having a biggest influence on the encounter rates. It was found that the most influential parameters were blade chord and blade speed. There are many limitations and caveats associated with the model outputs, and they do not take account of the avoidance and evasion behaviour that's expected from animals. Therefore, it's essential that we do collect in-field monitoring data to validate the models for use in the future, particularly when we're looking at array effects. In terms of monitoring on the O2 device, there's a number of underwater cameras that have been installed in the device in order to look at the rotor area and capture any footage on the near-field behaviour of these species of interest. A camera system had previously been installed on the SR2000 device, but unfortunately the footage has been deemed unusable due to the biofouling effects, as you can see from these images. However, an initial level of manual analysis has been performed on that footage, and this was performed through a NatureScot Commission project to review the tidal footage available across the sector and to capture any learnings. From that review, 2 assessment protocols were produced, and importantly, 36 recommendations came out of the review. These have all been taken into consideration when we've been doing the redesign for the O2 camera specification. Building on from the work in the FloTEC project and utilising the project recommendations, a progressive suite of environmental monitoring activities have been developed under the Horizon 2020 Forward 2030 project. And these will ensure that we're learning as much as possible from the environmental interactions associated with the O2 device and the O2.2 device in the future. And we'll ensure that the sector is learning from these as a whole and not just the technology developer. Under the project, an integrated environmental monitoring system will be designed and installed on the next device, which will include a multi-beam sonar and a camera system to detect and identify the species in the near field behavior and any near field behavior. We're particularly looking for that avoidance behavior. And this will then be used to inform future collision risk modeling when we come to look at array effects. And then we're also going to be looking at displacement behavior as well. So we're going to be undertaking further development of a predator-prey interaction model based on what the potential hydrodynamic influence of the device is and whether or not that will affect particularly fish behavior within the ecosystem. We'll also be installing hydrophone arrays to track vocalizing marine mammals across the site. And then finally conducting mobile fisheries acoustic surveys to investigate the influence of fish distribution and biomass. We're looking forward to getting started on this really exciting project, and we'll make sure to include any lessons learned from the FloTEC project, particularly in the initial design phase for Forward 2030. So thank you very much for listening. I'd now like to hand over to my colleague at Orbital Marine, William Annell, who will be discussing lessons learned from the construction and operation phase.
Thanks for the handover, Caitlin. That was really interesting. So I'll now be running through some of the main lessons learned across the project. As you have heard, the project has been a collaborative effort from partners right across the European supply chain. And without their dedication to the project and personal motivation, this would not have been possible. And so throughout the project, we had a lot of support, but even after the project, we've been well supported after the delivery of their scope. So after the launch of the O2, we conducted lessons learned sessions with all the main partners to feedback into future builds. And these exercises that we conducted internally and externally produced over 500 lesson notes across all the major disciplines, ranging from electrical, mechanical, fabrication, hydrodynamics, commercial and build management. So one of the first major kind of lesson areas to cover is in the field of construction. So it's a very important area for us to develop our learning, and we tried to develop that quite early on in the project. As you've heard, we tried to develop a flexible build program and contracting strategy that could be scaled up for serial production and arrays. The main point here that we learned just on the construction itself was that are just the usual fabrication bread and butter rules of thumb. Minimize overlapping works, minimize the number of manual whiles, do as much as you can indoor, and importantly, be strict about quality standards right from the get-go, and use inspection and test plans as much as possible to control the job. All these things that if you put in the groundwork early on will make the whole project run a lot smoother. Another big lesson on the construction side of things is that you have to integrate the design and construction teams so that the contractor can be really well supported with answers to any technical queries, any help that they need developing plans, and also so that there's feedback into the design team and they understand all the issues that are coming up in fabrication. There's plenty of times that it's very easy to design something on the computer, but in real life, it becomes apparent that there's other additional issues that are difficult to consider without that hands-on feel. So it's also important to use 3D modeling to help with this, to de-risk assemblies that involve multiple disciplines. Areas such as cable penetrations and cable routing can be particularly troublesome. So mechanical engineers are normally doing most of the design work, so we're always more interested in the steel work. But this time we put a lot of work into doing detailed modeling of cable routing and cable penetrations, and by modeling it in 3 dimension, you can really get a feel for things and problems that might occur. obviously this is a resource dependent issue, but thankfully we had a lot of support and a lot of hard-working members of the team that was able to fulfill this requirement. And we also learned that the best way to support complicated assembly procedures was to develop storyboards using 3D models and then present that to the fabricator or whoever was doing the assembly work. And this provided an efficient way to review the options, plan the procedure, and identify issues well in advance. Quite often you can be dealing with people that are used to 3D models. You can be dealing with people that work on on pencil and paper basis, more traditional means of doing things. So you kind of have to bridge the gap there. The next area that we have tried to make significant learning is in the field of operation, and we've made developments in the pitch controller algorithm that have resulted in a 20% drop in blade bending as we begin to approach rated power. So you can see on the graph on the top there. And we've also reduced the pitching activity by around about 40%, which greatly extends the life of the pitching mechanism. So you can see in the bottom one there, there's an overall reduction between the original and then the developed curves. And all this work has been done using on-site data from the point of installation till now. So we're still continually doing that exercise. This side shows how the controller uses torque control in the lower speeds and then switches to pitch control as we approach rated power and beyond. And this functionality has been validated during the ongoing generation activity. So you can see on the left-hand side, so we've got a cut-in speed of around about, can't see it on the graph, I just started 1, but around about 0.5 meter per second, and it goes up and around about this 2.5 meters per second, we start to switch over to pitch control. So that's the really tricky bit. And as you can see from the graph there, there's a nice smooth transition in power generation, and then onto a flat line there. So that's really what we're looking for. The next one, again, in the operational field, is that we've been working now with the nacelles and hubs, which are in operation, and we're getting back this real world data, and this is all verifying the performance of the power trains, making sure that the loads are as we expect them to be, and all of this work is informing structural design optimization and our spare strategy through fatigue and wear calculations using this data. So all these sensors come back, feed into the design process. We can look at the leg traction loads, all these things, and rerun fatigue calculations using real world data. And that makes us absolutely sure, or at least with the best confidence that we can, that we've got our fatigue calculations correct. And then last is in the field of offshore. The work we're doing in the offshore fields is continually molding our strategy around array development deployments, making it possible to move on to the next phase of the industry. So load out with the turbine, installation of the moorings and of the tidal turbine, they all feed into this process of how do you build and install multiple units in conjunction with all the other vessel operations and anchoring activities that have to happen. We've also had some great learning regarding our on-site intervention procedures. We've proved that we can access the nacelles and hubs on site, and we're now assessing firsthand the predicted weather windows for access on the tidal site. And this really helps inform the cost of energy, the sort of mean time that it takes before you can intervene and carry out these operations. The major lesson learned concerning the offshore works is that land-based trial fits are absolutely essential. Check all the interfaces and then check them again. Everybody who's been involved in kind of construction and complicated assembly projects knows it's always the interfaces that are the ones that cause problems. And this is probably the most important lesson of the whole project, given the significant risk to personnel, reputation and budgets. So by doing these on land in a controlled environment, we can de-risk these offshore-based interfaces well in advance. And this was done to avoid a baptism of fire scenario. Mooring connector trials were a good example of this. We carried out trial fits so that we could check the interface and know the installation procedure would be well understood by all those involved. By doing this in a controlled environment, we were able to dimensionally calibrate the connection just via the use of simple shims. And when we were on the tidal site for the first time, this proved a vital part of getting the connection procedure to work on first install. And another important lesson is that it's very important to get the design and offshore teams working closely together. So you can see our mooring connector models here, Tam and Dan sitting on the mooring connector, so that the ops personnel can feed input back into the design stage, and that we also had their attendance at relevant factory acceptance tests, and we found this to be essential for their learning and for ours, and the same reasons as mentioned previously. So I'm just running on a bit, but the last lesson is not, as you can see here, is not that you shouldn't move a 680-ton tidal turbine over half a kilometre of demolition site. It's that if you need to, you have to build strong partnerships in order to do so. So in this operation, you can see that we're moving across the tidal turbine across this demolition zone, and we had to have the cooperation and support from 3 additional parties: Texo, Forth Ports and Graham's, and this resulted in load-out operation being carried out very safely and smoothly with no incidents. So yeah, you have to get on with each other, and above all, you have to enjoy what you're doing and enjoy work. So I'll now hand you over to Lisa, who will close out the session with some Q&A. Thank you.
Thanks, William. That was a really interesting presentation and nice way to leave it there in terms of the collaboration and enjoying your work. I'll just ask you to stop sharing your screen and ask everybody else to come back, put their cameras back on. We've got about 5 minutes to go through some of the questions that have been being asked. Thanks to all the presenters for answering some as we went along, so I'll pick up some that haven't been answered so far. We'll probably not get through all of them, but what we will do is answer any questions that haven't been answered today offline, and we'll upload the answers alongside the video next week when we publish that. So the most voted for question that was asked came in from Danny Coles. This is going to Will.
All right.
I'd be interested to understand how much the rotor diameter could be increased, assuming increased loading was no problem.
Okay, yeah, no, it's a very good question. So if you take out the structural headache, the main aspect is just trying to fill the water column with as much swept area, with as much rotor as possible. So you always need a clearance between the tips and the water surface for passing ferries. And you don't want to breach the surface as well, because then the load drops from the top blade, and then all of the load is being applied onto the bottom blade, and you're then ended up with this big bending moment acting on the main shaft unit. So it's predominantly water depth is the main one. So deeper sites we can get bigger rotor, shallower sites we're more constricted, but you're probably likely to find higher flow speeds. So it's a compromise. So we're generally looking at rotors that are kind of in the 16 to 24 meter range. That's the kind of general range that we're looking at.
Thanks, William. The next most voted question came from Kadir Oran. Well, he's asked 3 questions, but I'm going to take his first question here. What are the limitations or recommendations concerning the deployment site in terms of maximum water depth and maximum distance from the shore where the device can feasibly be deployed and operated? William, you're possibly best to take this one as well.
Yeah, so I mean, I kind of answered half of that before. So yeah, we're needing, kind of 25 to 45 meters is quite common. 50 meters, we can handle much deeper water depths than that. Distance to shore, again, it's depth related. So if you have a very shallow incline, a seabed, you'll probably have to be further away. Quite a lot of the time, high current speeds are found close to shore because there's constrictions in the flow of ocean currents. So, you know, we're talking in the region of kind of, you know, half a mile to a couple of miles most of the time.
Lovely. And just the very last question I'm going to ask before we wrap up came in from Don Smith. Again, it's been well voted for in the Q&A. What was the single most difficult engineering problem in developing the technology? And were there any issues you faced that you hadn't anticipated? It's a very big question and need a relatively short answer to it, so maybe answer in more detail.
That's a fantastic question, and I'd probably like to have a pint with you over that one and have a good chat. But main challenges were the new innovations. So the retraction system was the right pickle to get sorted. Dealing with the massive loads on the main shaft unit that act up through the retraction system, because it's such a huge weight that's supported up quite a distance. That was a right difficult challenge to do. But then, you know, other things that, you know, the kind of everyday stuff like cable routing and hull penetrations and, you know, getting the specs and standards right, all these things need, you know, considerable amount of work throughout the project as well. So and the structural optimization of the cells, SKF had a good lot of fun with that as well. So that's the concise answer there.
Brilliant. Thank you very much. So I think that's our time up for this webinar today, and so we'll draw it to a close. As I said, any of the questions that we've not managed to get to, we'll answer them offline, and we'll be publishing this webinar alongside the answers to those questions next week. Just like to extend my thanks to all the speakers. Really interesting presentations there to show all the amazing work that's happened in the FloTEC project and resulted in having a really quite amazing machine being operated at EMEC in the form of the O2. And thanks to everybody for tuning into this session, and hope you all have a good day. Thank you.